Hi, my name is Tayson. I'm really excited to talk about my first data science capstone project podcast. So this is a project where I completed from a Springboard remote online data science program. So let's get started with this. So first, let me share my screen. Okay. Okay. So the main topic of my capstone project will be cardiac stroke risk stratification using a classification model. So here is a brief agenda on what I'll be talking about today. So let me briefly talk about the background statistic about the cardiac stroke within the United States in 2017. So first of all, cardiac stroke actually account for 1 in 20 deaths. And second, among all causes of deaths in the United States, it actually ranked number 5. Third, about 795,000 people experienced a new or recurrent stroke event. And then finally, the estimated indirect and the direct cost for the stroke treatment is around 52 billion US dollar. So why should we care about this problem? There are a couple of things that I actually wanted to highlight it. So first, stroke is a preventative condition. So basically what that meant is with the proper management of the lifestyle behavior, such as the exercise level and the dietary behavior, one can actually improve their outcome. Second, there has been an increase in projected percent of people having more stroke in the United States. Finally, third, increase in cost for the stroke treatment becomes an overall trend over time in a recent year. So the potential stakeholder for this project will be the first, the hospital cardiac unit managers and the group of clinicians. Second, the insurance companies and the policymaker. Third, employer groups for the patient population. So the main goal of this project is to predict patients with the high risk of developing a stroke condition. So there are two main objectives. First, help group of clinicians to take proactive health monitoring. Second, target prevention on patients with the high risk for developing a stroke condition. So now let's talk about the data set overview. So this data set actually comes with the 11 set of info feature for predicting a one stroke label. So there are about 8 categorical and the 3 numerical features, which contains information about the lifestyle and the health demographic indicators. And the overall sample size of this data set is around 43,000 observations. And then here is a snapshot you could see in the middle, which contains 11 set of the input features and the one class label. And there are some major challenges with this data set. So first is the class imbalance. So there are about 98% of our data set, it's non-stroke cases, and only 2% of cases were the stroke cases. Second, there are some outliers and the duplicates. And third, finally, there are some missing values on the certain set of features. So now let me talk about the data wrangling step, because data wrangling step is mostly focused on the data cleansing and the feature transformation. So the data wrangling can be broken down into 5 major steps. Step 1, we load the raw data onto the Python as a data frame. Second, once the data gets loaded, we're going to treat the missing value replacement. So depends on the situation. You could actually do the feature dropping a feature. So for example, if on the certain set of feature, if the data is actually missing more than a 50%, for example, we'll just simply drop that feature, like that column, because it's not going to add any value, meaningful value, even if we actually imputed them. So on the remaining set of feature, we're going to use a feature imputation technique using a measure of central tendency, such as mean, median, and mode. And depends on the type of feature we have, as a numerical or the categorical feature. So once the missing value gets treated, third, we're going to execute the handling outliers. So if we look at on this slide, the right sub figure represent the graphical representation of box whisker plot. So box whisker plot is basically a tool that tells us mean, median, maximum, and the first quartile and the third quartile. So using this information, we can calculate something called interquartile range, which is simply subtract from the third quartile minus fourth quartile, being 75th percentile, minus the 25th percentile. So using this interquartile range, we can actually compute the lower bound and the upper bound threshold. So basically what happened is if any feature value sits below or above the threshold, they will be treated as an outlier. Then we'll just simply remove them from the entire data set. So once the outliers get handled, then first step, we're going to execute the resampling strategy. So resampling strategy is a major player on this problem because as I mentioned earlier, our data set is highly class imbalanced. So we want to actually take a downsampling approach, basically taking a negative subsampling on the majority of class being non-stroke cases to make a sample size of non-stroke cases equal to the stroke sample size. Then we're gonna end it up with the 50%, 50% on each cases with the same proportion. So once the resampling is done, then we're gonna perform a feature transformation. So feature transformation can be described into three minor steps. As first is a feature encoding. So basically what we're gonna do is convert the categorical features into a numerical format that can be easily understood by the machine learning model. Then second, we're gonna execute the feature engineering. So using a set of existing feature on our data set, we're gonna generate a new feature. Then finally, feature scaling. So feature scaling is a crucial step. Basically, we're applying a scalar function such as min, max, or the log, etc. Then what it does is it's going to bring the different range of the feature on our data set within a similar range of scale. So this is very crucial because some classification algorithms are basically sensitive to the Euclidean distance. So overall, it helps us to improve the accuracy of our model in a better fashion. So now let me talk about the entire model workflow. So for our classification model, it actually can be described in two stages. So stage one is focused on the model training and tuning. Stage two is for the model performance estimate. So on the stage one, we load the raw data onto the Python. Then we execute the data wrangling step, as I mentioned it earlier. Then third, we're going to perform a data partition step. So in the data partition step, we're basically splitting the original data set into training, validation, and a test set with the proportion of 50, 30, 20%, as for example. So with the training set, we're going to build our model. Then once the model gets built, using a validation set, we're going to validate our model performance, basically optimize and tune our model parameters on each classification model that we choose. Then finally, once the model gets completely trained and validated, we're going to use a holdout test set to basically compare different classification model that we choose. So now, let's move on to the exploratory data analysis phase to uncover some of the interesting insights that I gather from this project. So in terms of distribution, basically on this slide, as you can see here, is that I plotted the histogram in terms of age, body mass index, and the average glucose level for both stroke and non-stroke population. So the main take-home message here is that in terms of age, majority of stroke patients were senior, meaning that you could see on the histogram, the orange histogram, the distribution is actually skewed to the left. And second, in terms of body mass index, both non-stroke and stroke population actually shows a normal distribution pattern, where their value is centralized somewhere between 25 to 30. And finally, in terms of average glucose level, both population actually shows no normal distribution pattern. But what's very interesting is that if we look at the stroke patient population of that histogram, it shows some kind of bimodal peaks on the lower and the upper range of the average glucose level in terms of distribution. So now moving on to the lifestyle factor. So here are the 4 different bar charts that are plotted for each lifestyle factor. So in terms of occupation ratio, both stroke and non-stroke patient population were employed mostly in the private and the self-employed sector. And second, in terms of marital status, there seems to be more married patient than being a single patient for both stroke and non-stroke population. And third, in terms of gender ratio, it's quite interesting that both stroke and non-stroke population, there seems to be more female patient than the male patient. And finally, in terms of urbanization ratio, both stroke and non-stroke population actually shows equal proportional people actually live in the urban and the rural area. So now moving on to the health indicator factors. So here are the 6 pie charts that are grouped for stroke patient population and non-stroke patient population. So first of all, in terms of smoking status, it seems that there are more stroke patients who are actually a smoker in terms of ratio compared to non-stroke population. And also in terms of history of hypertension, the ratio of the hypertension is actually higher on the stroke patient population than the non-stroke patient population. And also with the history of heart disease, stroke patient population seems to have more heart disease history than the non-stroke patient population. So now, this is a correlation metric. So a correlation metric is a tool. Basically, it tells us that including a set of independent and the dependent variable feature to describe a correlation, the relationship. So the take-home message here is that the age seems to be most significant predictor for predicting a stroke label with the correlation value of 0.59. So this actually indicates the strong positive correlation between the age and the stroke, the output label. So now let's move on to the model selection and the result. So in terms of model selection, I actually ended up testing 4 different classifiers. So first model is a logistic regression. Logistic regression is basically we're using a sigmoid logic transfer function to basically transform the initial input feature values and calculate the estimated range of a probabilistic range of our outputs, which is the stroke label, to become 0 to 1, which indicates 0 being a non-stroke, 1 being a stroke cases. And it works really well on the linearly separable classes kind of problem. So second is a decision tree algorithm. So the decision tree, what it does is it actually split the data on the feature, and actually it repeat this splitting procedure in a repetitive fashion. And then it continues to split until each tree node left with the same class label, either being non-stroke and the stroke cases completely. Then third is a random forest. It's a type of ensemble learning technique. It creates basically many decision tree and then average the performance of tree on each observation. Then the fourth is finally a gradient boosting technique. It's a sequential type of training technique, so it actually does it in a stepwise forward fashion. So basically what it does is from each iteration, it tries to learn from the residual error of the previous model to improve the overall accuracy of the model as it actually moves forward. And finally is the majority vote classifier. This is ensemble learning is a type of meta classifier. So basically on this model, I'm combining all 4 models that I tested to improve the overall accuracy of model performance by taking a majority vote from each model for each observation. So now, feature selection. We all know that in our data set, not all of the features are going to be useful for building a good accuracy classification model. So basically, on some of the classification algorithm, it actually supports the feature importance module. So basically, in this feature importance plot of the XGBoost model, the take-home message here is that the top 3 selected feature, the most important features, were the body mass index, average glucose level, and the age. So now moving on to the model comparison. So here is a summary table chart describing the 5 different model performance in terms of the evaluation metrics being accuracy, precision, recall, and the ROC score. So overall, in terms of evaluation metrics, the best performing model was a majority vote classifier because it actually achieved the 80% accuracy. So now this is a confusion matrix for the majority vote classifier that I created. So the interpretation here is that the about 80% of correct predictions were made on both stroke and non-stroke cases. And then there are about 20% of misclassification errors are made on both stroke and non-stroke cases as well. So the take-home message here is that there needs to be fine balance between the machine learning model and the human intervention is required, especially on the 9% error, which is a type 2 error for false negative, because so these are the cases where model actually predicted as a non-stroke, but in reality, these cases were actually stroke cases. This is really bad in clinical or the medical practice, because if we actually ended up missing these patients, this can actually lead to the more complexity. In a worst case scenario, reduced mortality rate of the patient. So here is another representation of similar information using a log and the precision recurve curve. So left is a log curve basically plotted for all five classification model. So the take-home message here is that in terms of the majority voting classifier, the area under the curve is actually indicated as a 0.86. So basically what that means is about 86% of time, this model is actually good at separating the stroke cases from the non-stroke cases. On the other hand, on the right side, it's actually showing a precision recurve curve for the majority vote classifier model with the average precision of around 82%. So meaning that about 82% of time is actually good at making a stroke prediction from the total number of actual stroke cases. So here is an overall summary. So the goal was to actually predict the cases at the high risk of developing a stroke by a classification model. And the results were the model was able to predict whether or not the patient were at risk of stroke. And then 80% of accurate predictions are made on the test set of stroke data. So in terms of risks, model incorrectly classified with 9% of error as being likely patients are non-stroke, but in fact, they actually had a stroke. So the mitigation strategy here is that we need to identify these cases with the group of subject matter expert clinician before making any clinical decisions. So the next step will be collection of meaningful feature and the model improvement, which I'll discuss it in later with the future works and limitation. So in terms of future works, first limitation, there are some absence of useful feature or attributes. So what I mean by that is instead of having a categorical feature as smoking status or hypertension, it would have been actually useful if they actually measured the blood pressure level with the exact numeric value. And the second thought is that there seems to be weak feature interaction between a categorical feature, such as smoking status and hypertension, etc., other than those age, average glucose, and body mass index to explain and interpret our classification model. So the future work will be the first, the collection of meaningful feature, meaning such as genetic predisposition and physical activity. Especially, I want to talk about the genetic predisposition because when I was analyzing the stroke patient population, there are a few minor cases where the age of the stroke patients were actually are younger than age 10. So which is really hard to explain with the existing feature other than the genetic factors. So in terms of the model improvement, there are a lot of different approaches that we could actually take into account. For example, stacking and other ensemble learning techniques such as ADA boosting, etc. And third, in terms of resampling strategy, there are other resampling strategies such as SMOT and the oversampling. And finally, in terms of the model design, instead of designing one classifier, we could actually divide it into age stratified cases to build a two classifier for younger patient cohort and the senior patient cohort. So here is my full recommendation after executing this capstone project. So the first recommendation is add a stroke screening test at a recommended age before 65. The reason is age 65 because the mean age of stroke patient population are around 65. And the second is a collection of meaningful features such as stress level, physical activity like exercise level, blood pressure measurement, and other genetic factors. And third, conducting a cohort study with the feature engineering technique to further stratify our existing patient data set, like our patient cohort, into diabetic or non-diabetic group using a body mass index and the average glucose level feature to further divide them and investigate our data set. So thank you for listening to my first data science capstone project podcast. I would like to hear any thoughts and opinions and questions on my YouTube channel. And thank you for listening. Thank you so much.